think it's time we get started. So welcome to math class. So the second half of this course, or the part 2 of this course, is going to go kind of more into the theory and the math behind the programs that we write. So we're going to start that off by introducing a few concepts on like how we measure a program's runtime. So back in 61A, all we were trying to do was get you to write programs. Like if you can write a program that works, like that was all. We were happy with that, that's enough. But we are not just programmers now. We are engineers. And as engineers, we don't just want something that works, we want something that works efficiently. So there's going to be two main ways that we consider efficiency. The first way is kind of like how efficient it is to write your code. So 61A was all about writing code efficiently. Like, can you write your code quickly? Is it easy for you to understand? Is it easy for you to change that in the future? That's actually kind of important. It's a lot more important than you might think. As it turns out, the majority of the time that you spend writing your code isn't going to be in just writing out your first algorithm, but in debugging, or in fixing code, or in rechanging your code to like fit some new problem. Like, the majority of your time is going to be spent taking your code and revamping it to be something else. And to do that, you need to have code that's easy to read and easy to understand. So what we'll talk about today is actually going to be the execution cost. How fast is it to run? So once we write a program, we need to figure out, like, is it a fast program? Does it actually work effectively? How much memory does your program use? How much time does it use? Those are going to be our two main metrics on how good a program is. So in order to talk about this, we're going to cover this algorithm here. So we are going to be given a sorted array. So this array is in order from smallest to largest. And our goal is to figure out if there are any duplicate numbers. So in this example here, are there 2 duplicates? Are there any duplicates? Yes. What's a duplicate? Yep. We have 2 4s in the middle there, right here. And so we should return true on this. If one of those 4s was a different number, we'd return false. Now, how can we solve this? Does anyone have any algorithms on how they could solve this? Randomly return true or false. Is that a good algorithm? No. I think that's going to have a 50% error rate. I want 100% success. Start at the first number, check against every other number, then go to the second one, check everything else. Yeah, we could do that. We could consider every possible pair, return true if any of these 2 match. That's a bit, yeah? Yeah, since it's ordered, another option is that we can just check every adjacent one. Since everything's sorted, if there is a pair that matches, then they should be right next to each other, like these 2 4s. Which one do you think is better? Version 1, where you check every pair, or version 2, where we just check adjacent ones? How many people say version 1? 2 people. How many people say version 2? Everyone else, including the 2 people. All right. So, yeah, the second one's better. How better is it? That's the question for today. So here I have these 2 codes. Dupe1 and Dupe2 are written over here. And we want to figure out a way to say Dupe1 is conclusively better than Dupe2. Is this large enough? Do you want me to zoom in? You remember how to zoom in this? Or increase the font size?
No, that's why I asked you. I think it's okay, because the code itself doesn't really matter, right?
Yeah, not particularly.
Okay.
All right. High contrast. Yes, high contrast. What was the high contrast? How do you?
So you go, it's the IntelliJ button, and then settings. Or file, I think it's fine.
File.
Settings.
Settings.
Yes. And then it should have
appearance. High contrast. Ooh. That looks way better.
Okay, we're good, we're good.
Wait, what
You
happens?
can also zoom if you want to make it larger, but I think it looks good.
Does this work? Is this slightly bigger? I think this
I
slightly.
think it's good.
All right, let's keep going. So our goal here is going to be to find some way to mathematically show that dupe 1 is better than dupe 2. It should be simple. We should be able to tell at a glance what we're saying is true, and it should be mathematically rigorous. Like a mathematician should be able to say, yes, this is definitely true, and it should definitely show that dupe 2 is better. So how do we do this? Well, one approach, just time it. Let's try doing that. So we could have a physical stopwatch. Unix actually has some commands that let you do this. So for example, over here, I have this code. And what it does is it creates a stopwatch. It's kind of like starting a stopwatch. It runs this code. And then it checks how long that took. So using this, we can see how long the program took. And then after this, we just print it out. I have this set inside a loop that just doubles the size of the object every single time we run this. Let's see how long this takes. All right, so for size 1,000, it's instant. Size 2,000, 4,000, 6,000, or 8,000, it's all about the same. But it gets really slow really quickly. I have this set up, so I think the next one's going to take like 20 seconds. But let's see. As we can see, as we get larger, it takes longer and longer time to go through. That kind of makes sense, because like when we have a larger array, we have more pairs to look at. It takes longer to run. So based on this, these tests, it started off really reasonable, right? 0.06 seconds, 6 milliseconds, that's time. You got plenty of time for that. But 21 seconds for a 512,000 long array, that takes forever to run. Let's copy this over here, so we have this. And let's see what happens when we do dupe 2. And if we run dupe 2, ooh. So as you can see, this is way, way better. We're already at what? 524,288,000 items. In fact, it's so good that the problem isn't the fact that we have a runtime that's slow. The problem is that we run out of memory to store our list. So this ends up breaking in terms of we ran out of memory before we run out of time to run. And as you can see here, all of these were like very, very short times. Like we could get really close times. Like this is basically as fast as we need. We don't need any better. So we could say that. Are there any problems with that approach? Yeah? Yeah, you don't always have a stopwatch. Yeah? Huh? Yeah, if you run out of memory and then you do a second run of this, then it is going to be much slower. That's kind of out of scope for this class, but that is true. I think we can formalize this by saying that if we run this multiple times, then we're going to get slightly different values. Like, let's say that I run dupe 1 a second time. Here, 1.336 for the 128,000 one. This one was 1.444, right? Those are two completely different numbers. It's like a 6–7% difference. And that's just because I ran it a second time slightly later. Because my computer is running some other stuff. Maybe it's more busy at that time. There's so many different factors that can affect the time that it's not going to be exact. Any other problems here? Yeah? Yeah, different computers are going to run different times. Like if I run it on Perrin's computer, it's going to be, how old's your computer?
Not this one, but I have one that's 10 years old.
All right, the 10-year-old one is going to be like way, way, way slower. Yeah. This one's like 2 years old, I think. So, yeah. So if we run it on a different computer, I'm going to get a different time. In fact, if I run it in a different language, I'm going to get a different time. here's the exact same code in Python. If I try running this one, right? Already at 8,000, it's taking a second. 16,000, it's 3 seconds, right? Did my code all of a sudden get, like, what is this? 16,000 divided by 0.022, that's basically a factor of 100. Did my code get 100 times worse just because I switched to Python? No. The algorithm stayed the same. The only difference is I switched to Python. Incidentally, if I do dupe2 on this, same thing, right? It's really fast. The slowdown's actually happening because it's trying to create the array in the first place, and that takes so much time. Yeah. So as you can see, like, it's true that dupe1 is better or is worse than dupe2 on both the Python and the Java versions, but their scale is so completely different that just using a stopwatch doesn't really help us. It doesn't say enough. Here's how this was run, I think, one time we tried this. It was on a slower computer than the one I have, I think. And as you can see here, dupe1 and dupe2 yielded completely different behaviors. With dupe2, it was basically constant. It was like really slow growing. With dupe1, it just zoomed up really quickly. So while this was easy to set up, it also ends up being so affected by how things go, like when we run this program, whether we're running in Python, even what computer I'm running, that it's not really as useful as we'd like. Like, it's nice to know that on my computer, at this particular time, dupe1 was better than dupe2, or dupe2 was better than dupe1. But I can't say that's going to be true for every single other computer at every single other time. I want something that will be consistent across all cases. And you could play around with this and look for this. And one thing you would notice eventually, if you tried this out, is what happens when we take, what happened here? What happens if we take the,
Hover over it? Wait, like hover over the red real quick? Oh.
hang on. Ah, this is what I forgot. There. OK, I forgot a quote. OK, so if you just play around with it, then eventually you end up coming to this note, that if you take this, the time that it spent on this size, and divide it by the time you spent on the test from before, you actually get a number that's really close to 4. And it's not always, it's always very consistently close to 4. Same's true if you go over to this one. If I go to the Python one, and I do dupe1, then doubling the size also ends up being, oops. If I run this one, then it also ends up being close to 4. And that's consistent regardless of how many times I run this, where I run this. If I run this on parent's computer, it also ends up being this 4. Every time we double the size of the array for dupe1, we end up quadrupling the runtime. And that's regardless of where we do this. Meanwhile, for dupe2, if we run dupe2 under the same conditions, then this ends up converging to a number around 2. Same if I go over here and run dupe2. Yeah, this ends up getting somewhere around 2-ish. So that's an interesting observation we make. Like, if you just play around, then you end up getting to this point where dupe1 takes 4 times longer, dupe2 takes 2 times longer if you double the size of the input. And that's true regardless of where you run this, regardless of the language. It's all consistent. So let's try and see if we can find some mathematical reason behind this. So the second option on how we can compute this is by just counting how many times we do everything. let's count the number of times we run these operations on an array of size n. So the I equals 0 line, how many times does this happen if we run this code? Once. Yeah, we just run it once at this top. How about the j equals I plus 1 line? Also once. Well, not once, sorry. We run it once for every single time we go through this loop, which means that we have whatever this length is. In this case, it's 10,000. So we're going to go from 1 to 10,000 and call the j equals I plus 1 line exactly once each time. How many times do we run less than? Well, we have a less than over here. So that's happens like every single iteration. It happens every iteration of this inner loop, which goes from 1 up to 10,000. And then we have 10,000 up here. This goes really tricky. It takes forever to run. Eventually, you can compute that it goes from 2 to 50 million of these. The increments is also 0 to 50 million of these. There's so many of these. It doesn't really matter exactly how we compute this, but like, it's just so tedious to end up doing this math. Eventually, if you do this math, you end up with these numbers. So this is fairly nice. Like, this is independent of the machine that we use. It's independent of the programming language we use. So it's only dependent on the input. The problem is that this is just a pain to compute. And you know, if we pick the array size, like that was kind of arbitrary. Like, why did I pick 10,000? Like, should I have picked 10,000? I don't know. Like, what if you pick 100,000? It should yield the exact same results. And you know, this also doesn't tell you the actual time, how much it took. So what if instead of for n equals 10,000, we just computed in terms of n? So instead of making like a number, we get a function of n. If we do this, then we actually get fairly nice results. Instead of taking something in terms of n, we actually see how our algorithm scales, how slow it gets as our input size gets larger. The problem is, like, this ends up being even harder to compute. I don't want to do all this math. And this still doesn't tell you exactly how long things take. So just as practice, let's try doing this ourselves. For our dupe 2 version, let's try counting how many times we have less than, how many times we increment, how many times we do equals, how many times we access arrays. So first off, how many times do we do a less than operation? 10,000 times for n equals 10,000. What about for arbitrary n? N. Why? Yep. You run this for loop n times, so you go through n of these iterations. What about the incrementing? N times? Yeah. Why? Yeah. Because this inner part here, it happens every single time we iterate through this loop. When we do a for loop, we run this thing, then we check if this thing is true, then we run this thing if not. So we run this every time we run through this. What about the equality check? How many times do we do this? N. Why? Yeah, we do it once per loop, and we have n loops, so we do it n times. And what about array accesses? 2n. Why 2n? Yeah, because we do this twice. Are there any other operations that we're doing? My default speaker's changed. Hello? Does this die?
I think we can hear you.
Okay.
I'll just keep going. If people complain, I'll let you know.
All right. So there's actually a few more operations. We have some subtraction going on here. We have some addition going on here. But overall, for most of these operations, we can have these values. If you go through these, you can see exactly how many of these. It actually isn't always going up to n, because sometimes when we just find an equality in the first step, then we just return true immediately. So we leave the loop early. you know, sometimes we get lucky. So now if you did this and you just got few, like off by a few, that's fine. It doesn't really matter, these like off by one errors in this case. Like in the grand scheme of things, one addition is like 1 nanosecond worth of time, so it doesn't really matter if you miss one or two. Any questions up to here? Yeah? Can we elaborate on why Python was slower than Java? This isn't particularly relevant to this course, but ultimately Python is just a slow language. It's designed to be easy to write code in, which means that the computer has to do more to interpret what you're trying to say. And when that happens, it ends up being way more slower. Java is a compiled language, which means that what it does is it first translates all of the code into something that the computer can understand better, and then it does that. So to use an analogy, Python is like an interpreted language. It's like you're reading a book in like Japanese or Chinese, and then saying it in English to like someone. You're translating in English in real time. Whereas the compiled version is someone took that Chinese book, wrote it in English, and you're reading the English book. It's faster to read the English book directly than it is to be translating in time from Chinese. Yeah. Any other questions? Yeah. Huh? Yeah, Python is interpreted in C. Yeah, that is true. But that basically means there's a C program that's running your Python code. The C program has to do that translation in real time. Huh?
Keep it moving.
Keep it moving. All right. Fine.
It's interesting, though.
It is. So just looking at this, can we say quickly which one's better? Yes? Which one's better? Dupe 2. Why? Yeah, these are smaller numbers. 50 million is a lot smaller, or a lot larger than 10,000. But the better answer is, if I add all of these up, then we get something that's like n squared plus 3m plus 2 over 2. That's way bigger than n is going to be. So n is going to definitely be larger than this. A better statement is, I don't care about all of these. I care just about the fact that the n squared part grows way faster than the n part. N squared grows at a rate that's a parabola. As you get larger, it gets steeper and steeper, whereas a line just stays the same steepness over time. Now, when we cover asymptotic analysis, we only really care about the large input sizes. Like for those small inputs, like it ran in less than a second, it doesn't really matter too much to us if we're particularly efficient or inefficient. But if we have a lot of things, like billions of particles, billions of values, then that's when we start worrying a lot more about how slow things get. Generally speaking, we look for algorithms which scale better, so things that look more like lines, than things that scale poorly, things that look like parabolas. To kind of show this, let's look at an example here. Let's imagine that we have two functions that do the same thing. One of them takes 2n squared time to run. The other one takes 500 n time to run. So if n was, let's say, 5, ZIRP2, 500 times 5, that's 2,500 units of time. 2n squared, that's 2 times 5 squared, that's 50. 50 operations. So which is better, ZIRP1 or ZIRP2? How many people say ZIRP1? It took only 50 steps to do n equals 5. How many people say ZIRP2? It took 2,500 steps to do. Why are you saying the 2,500 one is better than the 50 one? Yeah, for these small values, ZIRP1 might be better, but as it gets bigger and bigger, like, it doesn't compare. Like, eventually, ZIRP1 is just going to overtake ZIRP2 by far. By the time we get to n equals 250, they end up being the exact same value. By the time we get to n equals 1,000, that's 2 million times for ZIRP1. It's only 500,000 for ZIRP2. ZIRP2 is 4 times faster at that point. Keep going up, that discrepancy only grows. We'll talk about this as like the order of growth of the runtime. So a parabola grows at a rate of n squared, a line grows at a rate of n, and that's largely the determining factor as to how long a program runs when we get to these really large numbers. So for n equals, for an theta of n, for an n runtime program, basically you can do it for whatever size you need. 10, 1,000, a million, that's like a second at a time each. That's fine. N log n, that's also reasonably good. N squared, by the time you reach this, if you want to deal with the size 100,000 thing, it takes 3 hours to run, which is just too slow to actually be reasonable. So if you get an n squared algorithm, an n algorithm is going to be way better. And if you can't even do n squared, if you need n cubed, you're going to be spending 32 years just computing 100,000 items, which will take forever. So if we did this, we can definitely see that dupe 2 was way better than dupe 1. Was this simple, though? Is it simple to do this math? No. Do you want to do this math? No. I don't want to do this math either. Let's not do this math. So we're going to have to find a better way to do this. Now, we're going to do a few simplifications to try and see what constitutes the core underpinning of what's going on. So in order to be simple, we need to simplify this, but we still need to maintain our mathematical rigor. So we'll be looking at every single operation that we do, and we're going to try to simplify things one step at a time. So our first step is we're just going to ignore our best case scenarios. We're only looking at our worst case. Why is this okay? Yeah, the worst case is kind of like the slowest possible thing. We kind of want to say like only that's important because like if it's better, then we just get lucky. We're fine with that. We will see some exceptions in this course, but in general, we do look only at this worst case runtime. In this case, for this duplication function, our worst case will happen when we have no duplicates at all. Those were the tests that we had running in the Java and Python. They were designed to have like no duplicates whatsoever at all. So this is already kind of simple. And let's just do a quick math check here. If we were to run this algorithm, what do you think the order of growth for this runtime for this function would be? I'll give, let's say, a minute. Feel free to talk with your neighbors. Yeah. How's Zoom chat going?
Not much.
Okay.
It's like super dead.
Why is there a lot of yeses at 1:30?
Since people wanted to know, you said they couldn't hear you, so I checked, and everyone said yes. There's not much. I don't think there's even any questions. All the questions were just, is today in scope times 5, so.
Wait, there's another question over there.
It was a slow day for me. Oh, someone pointed out it's just big O, and I was like, yeah, stay tuned.
Yeah.
They knew. They saw the vision.
All right, let's bring everyone back. How many people say A, it's linear? How many people say B, it's quadratic? How many people say C, it's cubic? How many people say D, it's sextic? All right, seems like the general consensus is cubic. And yeah, it's cubic. Why is it cubic? Well, this largest thing is an n cubed. All these others are smaller. And in fact, the reason why it's true is that as n gets larger and larger, if we just math it out, regardless of how long each of these independently takes, eventually this n cubed component is going to grow faster than all the others. An n cubed is just going to grow strictly faster than an n squared. So eventually any constant or coefficients ends up like becoming less and less important as n gets large. So this is actually true regardless of how long greater than, less than, or and takes. Like if you imagine that less than takes like 5 seconds to run and greater than takes 1 nanosecond, that's still fine. It just means that the less than takes 5 billion times a larger coefficient. But if n gets to like 1 trillion or quadrillion or 1 Google, then those n's are going to be way larger than even like a few billion. The billion kind of gets rounded off. So we can kind of ignore all of these lower terms. Like if we have this 0.000001 times n to the 2.00001, that's still eventually going to grow bigger than anything times n squared. So for sufficiently large n, only for a really large n, only that largest term is going to actually matter. We can just ignore all of these small terms because we're only looking at these really large n values. What else can we do? Well, if coefficients don't matter, then I can also ignore the coefficients. They're not going to affect how a shape looks. Like a parabola is still a parabola if you're doing 2n squared or n squared. Now, these coefficients can also tend to change when you define like what one operation actually is. Like what if you did incrementing by 2 steps, right? You take a number, you retrieve it, you add a 1, and then you store it back into like memory. Like that's 2 steps in a way. So you could imagine that the increment actually counts as n squared steps instead of n squared over 2 steps because you're treating increment as 2 steps instead of 1. You can do these kinds of weird things and show that basically any coefficient is reasonably true according to what you're doing. There are some branches of runtime analysis which do care about these coefficients. So this is not something you can say in all cases. Just for this class, we can just ignore all these coefficients. In 61C, you'll talk about when coefficients are actually important. But you know, those tend to be a lot harder because by doing this, we can also make this other simplification, which is that if just splitting up 2 different operations ends up acting as if we doubled the runtime and acts as like a coefficient, we don't actually care about coefficients, then we can just say, you know what? Every single operation we take, it's 1 time. Less than, that's 1 time. Increment, 1 time. Equals is 1 time. Array access is 1 time. Because even if an increment takes like 1 nanosecond to run and an array access takes 1 million nanoseconds to run, those are just coefficients. They're going to be removed anyway. So we can just count these as just 1 unit of time, 1 step. This also kind of lets us pick what we consider to be primitive operations, like what we consider to be the simplest operation that exists on our system. It does assume that our operations take constant time regardless of the input. Like adding together 2 5-digit numbers takes the exact same time as adding together 2 1 million digit numbers. That's not always true. In some systems, or in some versions of this, you do take this into account. But for this class, we assume that adding 2 1 million digit numbers takes exactly 1 unit of time, the same as adding 2 5-digit numbers. This will be known as our cost model. Through our cost model, we will say that everything takes constant time. Now, if we do this and do everything, then we've evaluated this complicated thing all the way down to n squared. N squared is a nice thing. It's very simple. I like n squared. It looks very nice. So I think this is a really easy way to, or this is a really nice way to simplify this. This looks simple. Let's see if this actually works. Let's do this for dupe 2. What is going to be our final result? n, why? Yeah, n is the highest power of n, and if you just do all this math, you just cut off all the worst cases, you ignore the lower order terms, you're ending up with a bunch of n's, you just get rid of any coefficients, and then you just add these all together, you end up with n. So using this, we can show that this is n squared, and this one is n time. Now, this actually explains kind of why we saw that 4 earlier. If we have a runtime equal to like n squared, then if we double the size of n, then 2n squared is the same as 4 times n squared, 4 times as large as the previous value. That means that if we double the size of an input, that'll be 4 times the longer runtime. That's exactly what we saw earlier. When we ran this on actual code, we saw that this averaged at around 4 times slowdown every time we doubled the array. So despite all of these simplifications that we made, we can see that this theoretical analysis matches this experimental value. And that kind of gives us confidence that we haven't lost any information about what's going on, that all of these things are mathematically rigorous and that they make sense. So doing this, we can just follow this process. We can create this table of operations, and then we just compress this table one step at a time down to this total that's n squared. Do you want to do this? No, why not? It's tedious. It's worse than earlier. We had to do the exact counts earlier. But if we can do these simplifications from the start, then we don't even need to build the table. We can just start off, look at it a bit, and try and see if we can get it to n squared. So let's do this. Instead of building the entire table, I'm just going to do this. I'm going to treat anything that takes constant time as a single operation. These are constant time operations. I don't care exactly what's going on. I'm going to treat them as 1 unit of time. I'm going to figure out the order of growth for that 1 unit of time, either by making an exact count or doing some intuition, inspection, trying to do some math. This last part's only going to be possible with a bit of practice, but you should be able to do some of this. And using that, we are going to get to n squared without building the entire table. Let's try doing this on dupe 1. And this time, we'll just show everything. So here's our code. And the first step I'm going to do is I'm going to say this inner thing, that doesn't depend on how long n is. Checking where an array is, it doesn't take anything in terms of n. Equality doesn't take in terms of n. Returning doesn't do anything in terms of n. I'm just going to say that's 1. That is 1 unit of time in there. Exactly 1, no more, no less. So how many steps do we run this 1 unit of time? Well, we can draw this kind of diagram and look at every single value of I and every single value of j that runs this 1 unit of time. And we can see that for I equals 0, we run from 1, 2, 3, 4, 5 up to n. For I equals 1, we go from 2, 3, 4, 5 up to n. From I equals 2, we go 3, 4, 5 up to n, and so on. We kind of get this triangle pattern that grows all the way up to n size. The exact total number of this is 1 plus 2 plus 3 plus 4 up to all the way n minus 1. Can we add this together quickly? Well, there are some tricks on how you can add this. The clever way that we do this is we kind of reverse this order. We add these two sequences together. 1 plus n minus 1 is n. 2 plus n minus 1 is n. 3 plus n minus 3 is n, and so on and so forth. So we get 2c is equal to n plus n this many times. There's n minus 1 of these. So that's n times n minus 1. And if we do this, c is equal to n times n minus 1 divided by 2. So using all of this math, we can say that there's n times n minus 1 over 2 units of time that this code runs. And if you split this up, you get an n squared as your total runtime. Any questions on the math we did here? This is somewhat tricky math. Yeah? So to get to m times n plus 1 over 2, what we kind of did was we kind of did this algebra. So we started off with c is 1 plus 2 plus 3 all the way to n minus 1. And then I said, well, since addition is commutative, I can just flip the entire order of these items. So I get m minus 1 plus m minus 2 plus m minus 3 and so on. And then we just added each of these pairwise. So 1 plus m minus 1, that became n. 2 and m minus 2 add to get n, and so on and so forth. Now there's a total of n minus 1 of these, so there should be n times m minus 1 here. And then if we divide this by 2, because this is 2c now, then we should get the value of c. Yeah? If we add this top part and the bottom part, then we add the left side, that's c plus c equals 2c. The right side, this plus this equals this. Yeah. Any questions or just stretching over there? All right. Now, another approach is you can just kind of look at it. This looks like a triangle to me, right? What's the area of a triangle? Yeah, 1/2 length times width. What's this length? N, just about n. What's this width? Just about n. So this is n times n divided by 2, or just n times n, which is n squared. So we can kind of look at it and say through some geometry that a right triangle is going to grow at a rate of n squared. And we can say, yeah, it's probably n squared. So yeah, you can do this more mathematically rigorously. You can actually show that this is true. But if you just kind of look at it finely enough, then you kind of see that it's an n squared runtime. Yeah, any questions here? Yeah, this isn't as easy to use as the just direct math approach. It doesn't work for everything, but for some things it does work. So let's formalize this not just for this like duplication function, but for everything. Given a function, we can apply these simplifications to yield this order of growth. So if we take 3n cubed plus n squared, what's the order of growth with this? N cubed. Yep. We just get rid of everything except for the most significant term. Let's try to show like a more formal notation to specify what we did. The math might be a bit complicated, but the idea is just the same. Like if you understand like the intuition behind what we were doing earlier, that's all you really need to know. You don't need to know this complicated formula. But it's useful to have it available. But before we do that, let's just do a few more examples. N cubed plus 3 n to the 4th. What's the order of growth of that? N to the 4th. Why? It's the biggest thing. All right, what about the next one? N cubed. Yep, n cubed is larger than 1 over n. What about this one? 1. Yep. Because the 1 over n grows smaller, the 5 is a larger thing, and 5 is just a coefficient. 5 is just 5 times 1. So we just say it's 1. We can say it's constant. Generally speaking, when we say constant, we just turn it into number 1. Yeah. What about this one? N e to the n plus n. N e to the n? What about this one? 4n squared. Why? Yeah, sign goes between -1 and 1, so it's going to be bounded by a constant. So the n squared is the only thing that actually grows here. Yep. So we're going to write this theta to signify what we're doing here. So when I say n cubed plus 3n to the 4th is in theta of n to the 4th, what I'm saying is that the order of growth of n cubed plus 3n to the 4th is the same as the order of growth of n to the 4. The formal definition is here. It's a mess of terminology. Let's just go through this one step at a time. What this is saying is that a function f is defined to be, or a function r is defined to be in theta of f if there exist these two constants, k1 and k2, such that this equation holds. So f of n is probably some simple function. K1, K2, you just pick some constant factors. And if r of n is less than a constant factor times f and greater than a different constant factor times f, then we say that r grows just about the same rate as f does. So in other words, r and f differ only by coefficient, effectively. And you only need this to be true for sufficiently large n. You can just pick some number, let's say 1 million, and as long as it's greater than this for all 1 million, then it's fine. As an example here, 40 sine n plus 4n squared is theta of n squared. Here we can say that r of n is this, f of n is n squared. K1 I can say is 3, because if I pick 3 as my K1, then 3n squared is always less than this thing. K2 can be 5, because 5n squared is always going to be greater than this thing. So if we had this function, we could do something similar. What is our f of n for this function? N squared? Yeah, the n squared is going to be bigger. What's our K1? Five? Is 5n squared always going to be less than 4n squared plus 3n times ln n over 2? Is it? 3? Well, let's kind of do this math, right? If we do 4n squared divided by 2, that gets us 2n squared plus 3 over 2n log n. I think this 2n squared is going to grow faster than this thing. So we only really need to care about the 2n squared part. But 3n squared is going to grow bigger than 2n squared. Huh? Sure, we can do 1.99. All right, yeah, we can just pick any number less than 2 for K1. What are our K2? 3? Sure, we could pick 3. And if we do this math, then we can show that this is going to be between 1.99 n squared and 3n squared for sufficient size. I picked 1 and 3. This doesn't actually change what we did, all this operations. The only difference is that we just use the theta symbol when we write our order of growth. So it's just a way to formalize this, show the math exactly, kind of specify what we mean, because order of growth is kind of like a wishy-washy term. It doesn't exactly have a defined meaning. Theta has a defined meaning. Now, we can use this to describe the rate of growth of a function. When we say the rate of growth of a piece of code, we're actually talking about the runtime as a function of n. So if we say a function is theta of n, what we're actually saying is that the runtime of running that function is theta of n. Now, sometimes we don't just have a theta bound. We can't figure out like a lower bound on how fast things go, or a greater bound or an upper bound. Sometimes we only have like half a bound. We know something's faster than this or something slower than this. And in that case, we can use big O and big omega. Kind of the analogy here is theta is like equality, if A is equal to B, whereas O is less than or equal to and omega is greater than or equal to. So here's our definition of theta. Just get rid of that other side, the left side, then we have big O. Get rid of the right side, we have big omega. So effectively what we're saying for when we say something is O of n squared means that it's going to be faster than n squared, or the same speed as n squared. And when we say omega n squared, that means that it's going to be n squared or slower. So here's examples of some functions that exist that are theta, O, and omega. Generally speaking, given any piece of code, you can try and figure out O bounds, omega bounds. Theta bounds tend to be difficult sometimes. Generally, we don't care about the exact runtime function. We only care about the order of growth. And generally speaking, the easiest way to do this is you just look to constant operations. You reduce these to 1 unit at a time. You count how many times we do this, and we generally look only at these worst cases. Now, we can use O bounds. Those tend to be used for upper bounds, like if you have a function that grows at least as slow as this. We will see some examples when we talk about disjoint sets. Omega, we don't use it too often, but it does show up in theoretical computer science. We'll show it when we get to sorting. Yeah. All right. If there are any other questions, feel free to come up. Otherwise, yeah, we're done.
Midterm review session on Wednesday.
Yeah, midterm reviews on Wednesday. Blue. Hello. So this was running. Test, test.